So you saw earlier a bit of the, let me see. Yeah, so you got a little preview this morning with the Q&A with Alan of some of the work we're going to do in material discovery. And in this talk, it's my pleasure to give you a bit of a deeper dive in what we're doing in that area. I want to begin by motivating my talk with what I believe is the quantum information science and engineering blind spot. And that's ultimately, analog quantum computing, quantum annealing being one good example of that type of computing model. So we heard about it this morning in the keynote, but there's a very nice paper called Quantum Computing in the NISQ Era and Beyond by John Preskill. It basically charts a perspective on where we are with quantum computing technology back in 2018 and where we would be going for the near future. In that document, there's a section on digital and analog quantum simulation, which is really relevant to what we're talking about here. Now, in the beginning, so I've pulled the key paragraph, which is section 6.10. This begins with a very interesting remark, which is that we can anticipate analog quantum simulators will eventually become obsolete. And based on this type of argument, I often hear from scientists around the world that analog quantum computing is a dead end. That leads to a very natural corollary, which is basically anyone who works in this field as a researcher is also pursuing a dead end, and it's just kind of a fruitless area. I think that's a really unfortunate attitude that I've experienced many times because of this last sentence in this very seminal paper by Preskill, where it says, therefore, when seeking near-term applications of quantum computing technology, we should not overlook the potential power of analog quantum simulators. And in this talk, I'm going to show you an example of how that power potentially can influence near-term applications. So this is how I feel about the topic. But still, to try to help me communicate with other people in the community, I decided to pull the thread. Let's just presume the hypothesis that one day gate-based quantum computers will make quantum annealers obsolete. And let's see, when might that happen? What types of gate-based quantum computer would it take to make that happen? So we recently released this paper on the archive, The Cost of Emulating a Small Quantum Annealing Problem in the Circuit Model. I should say thanks to all my co-authors on this paper. We all contributed very significantly to this work. It's a very interdisciplinary paper with a lot of interesting results in it. But I'll try to give you the highlights that are relevant to this talk. So in this paper, we study a 4-qubit model, which you can see pictured on the slide with the circles and the edges. That model is really small and it's easy to simulate with a classical computer, and that's why it's a good tool for investigating, what type of quantum computer would it take to replicate this obviously trivial experiment. The figure just below the circles and the edges, which you see, is the quantum dynamics that occur in this model as you change the amount of annealing time that you use. So in the beginning, it's like a straight line because everything is in a uniform superposition state, but after you anneal for a long enough amount of time, you have these exotic oscillations and then convergence to a very particular signature, which is interesting and measurable. So we can classically simulate this. That's what the picture on the bottom shows you. And we just ask the question, well, what type of gate-based quantum computer algorithm would it take to reproduce the results in that figure? The core computational block is the kind of gate circuit that you see in the center of the slide. It has some rotation gates and then some 2-qubit gates. There's 3 2-qubit gates. And this particular circuit, which is 4 layers deep, based on current superconducting qubit technology, takes around 1 microsecond to execute on a gate-based quantum computer without any error correction or error mitigation or other kinds of overheads. If you look at the table below, you can see how that runtime compares under different amounts of annealing time to what you can do on a gate-based system versus the annealing-based system running at a gigahertz energy scale. So if we want to simulate one algorithmic time unit, it takes about 5 repetitions of the quantum circuit I showed you there, and that will take about 5 microseconds because each block takes 1 microsecond. If you're running this at the gigahertz scale in an analog quantum computer, it takes approximately 1 nanosecond. Again, if we can just zoom all the way down, it kind of increases by orders of magnitude as you increase the amount of annealing time you want to simulate. But if you look at the bottom row, it's like 1,000 time units requires about 1,000x nanoseconds or 1,000 microseconds. So in all, this looks like 1,000x runtime gain that you would have to do this on this kind of gate-based quantum computer. You would have 1,000x slowdown. So then we took the experiment a little bit further and we said, okay, what would it take to reproduce this paper that D-Wave published, which you can run on the 5,000 qubit system right now. And that's a pretty big experiment with 5,000 qubits and about an evolution time of about 30. And if you just look at how many gates that would take, it will take thousands of gates, which means it needs essentially a fault-tolerant quantum computer, gate-based quantum computer to be able to implement this computation. And so if you do a runtime estimate for that fault-tolerant quantum computer, under optimistic assumptions, it would take about 1,000 seconds of like real wall clock time. But this same experiment can be run on D-Wave's hardware today, and it runs in about 1 second for one shot, right? So to me, this all points in the direction that these analog quantum computers will always have a runtime gain over the gate-based ones. They're a highly specialized type of device for very specific computations, so it's not surprising they would be faster, right? So I think because of that, for the classes of problems which you can solve on these computers, they will be useful for the long run. So turning now to what do we hope to use these things for at a place like LANL, we're all sitting around the computer. It's very much like the dawn of the classical computing age. We're like, what does this thing compute? What can we use it for? How fast does it run? And that leads to a natural question, like what will the killer apps be at LANL for quantum computation? The short answer is that it's not very different from many other scientific institutions. Simulation of quantum physics is a big challenge we have computationally in materials and chemistry. Producing things like these phase diagrams or other important structural properties are very time-consuming to do with classical computers. So this is like the natural application at a place like LANL. But one of the interesting questions out there is, what are we really going to do with it? A lot of the community has been focused on quantum advantage demos, quantum supremacy demos. You've seen some discussed earlier today. But there's actually a really interesting thought experiment. Like after we've done all the demos and we've all been convinced these computers can do things which no one else can, well then, what are we going to use it for? And that's actually a pretty hard question to answer. So at Los Alamos, we've been thinking about flagship scientific discovery applications for many years. And I think it took us about 5 years to come up with a really good answer, which is what I'm going to talk to you about today. And I hope that the time will be much faster now that we have better understanding of what the technology is capable of. But that gives you a sense of how difficult it can be to really answer this question. So let's talk about D-Wave for quantum simulation. We were very inspired at Los Alamos by these 2018 papers from the D-Wave team, which looked at doing essentially condensed matter theory experiments using their device. This was before coherent annealing. This was before their supremacy demo. But still, there were cases where you were sampling from interesting quantum distributions and you could reproduce important condensed matter theory. This inspired follow-up work at LANL, this Qubit spin ice paper and magnetic phases in the Penrose lattice, which was led largely by Alejandro Lopez and Cristiano Nisoli at LANL, showing that yes, indeed, we can continue to discover interesting condensed matter theory on D-Wave's platform. But my question was, how are we going to take this to the next level, right? Condensed matter theory is great, but we've done a lot of theory demonstrations now. That is well established. What can we do next to really have a big impact? And after putting a lot of heads together between scientists at LANL, we came up with this idea of doing scientific discovery in quantum magnets. Let's talk a little bit about magnetism. I am not a physicist by training. I'm a computer scientist by training, so this was all new to me. I'll try to give you the crash course. So Magnetism is really, the primary use case we all know is ferromagnetism. So that's like, magnetic hard drives or, electromagnets to confine plasmas. These are kind of useful but boring magnets. We understand how they work well. The interesting magnetic science questions these days come from very frustrated magnetic systems. So in the picture, you're seeing an example of when interactions within a lattice cause spins to be frustrated and not know if they should be up or down. That's when you start to have the really interesting behaviors. These things yield things like quasi-particles, excited states, weird phases of matter called spin liquids. And these are particularly interesting in the quantum regime where you can have superpositions of states. Some potential applications of these frustrated magnets are like next generation storage technologies or magnetoelectronics, piezomagnets, interesting sensors, and even potential superconductivity types of properties. So this is what scientists in magnetic materials are wondering about all day long. To help answer those questions, we have built large experimental user facilities. So at Los Alamos is the home of one of 3 sites for the National High Magnetic Field Laboratory. So this is a facility where they can cool down magnets and inject them with huge amounts of energy to see their properties and understand their materials behavior. It supports over 1,000 scientists a year to do their research from over 200 institutions and produces on the order of 400 papers per year. So this is a valuable scientific activity that we're doing as a nation. What does the Mag Lab do? There's a pretty impressive set of equipment, but essentially they take magnetic material samples, they prep them in a particular device, then they have these cryostats, which they can use to cool down the materials so that when they hit them with a huge amount of energy, they don't explode. Sometimes they do explode, but that's not ever intended. And then we have this massive generator, which is actually collected from 3 Mile Island to produce a huge amount of energy in big spikes to put into these magnets. The ultimate outcome are different types of observations. What you're seeing in the bottom right is an example of a phase diagram that was generated from real experimental data where they sweep magnetic field and temperature and try and observe like what phase the particular material sample is in. So abstractly, we can think of the protocol of the Mag Lab as you have this cryostat with a sample in it, you have a sensor which is measuring, say, net magnetization, and then you can apply a field to different parts of the sensor, like a Z field or an X field. And essentially, the graph you're seeing on the right there is a time-varying protocol that they would run in the lab, where first they would cool down the sample, that's the blue line, and then once it's cold, they would expose it to a time-varying magnetization protocol, like this up-down sweep. And by combining bunches of different protocols that they run on the magnet with what the sensor sees, they're able to produce insights about what the material's behavior is and what its properties are. So what is the value proposition for quantum computing for a facility like this? Ultimately, they just want to understand better with simulation what the materials are doing. So in the right of the slide here, you can see the top figure is a current classical simulation of a given material, and the bottom is the phase diagram that you get out of real material sample. So maybe they're qualitatively similar, but not quantitative. There's quite a big difference. And currently, no classical methods that we know can reproduce what we really observe in the laboratory. So the hope here is that some new quantum computations will kind of fill the gap between what we can simulate now and what the phase diagram that occurs in the laboratory can produce. So what does this all have to do with quantum annealing? This is a quantum annealing conference after all, right? let me take you through a specific example, which was mentioned earlier actually in Andrew's talk as well. So this is calcium cobalt oxide. This is a particular magnetic material, which they've been studying in the Mag Lab for some time. The important thing about this material is that it has a kind of an Ising model property, which makes it a really good fit for the type of simulation you can do on D-Wave's platform. What you see on the left here is the real data coming from the laboratory. So this is the hysteresis curve. You're doing kind of the upsweep of the data followed by a downsweep. And then you get a bunch of interesting signatures in the net magnetization. The y-axis is net magnetization here. And the protocol that's being run is on the right. So the thing that makes this particular magnetic material really fascinating are the three plateaus that occur in the upsweep. So if you look at the right-hand plot, you can see there's those three plateaus there. These are unstable states, which are not predicted by the ground state of the material or like the lowest energy state. And to be honest, we don't really have a good explanation of why they're occurring. There is some data using quantum simulations on the left, which also indicates that these plateaus could exist. So that's a hint that maybe there's a quantum mechanical effect going on in these states. That's kind of the state of affairs without quantum computing. What piqued our interest is that some years ago, there was a PRX quantum paper that was developed by D-Wave and others, which studied the same material, but using the D-Wave 2000Q system as kind of a surrogate model for the material's behavior. So they took the D-Wave lattice, they encoded the lattice of that particular material, and then they tried to replicate this particular protocol, but using a very clever idea, which was that we're used to doing forward annealing in the quantum, on the quantum annealer, which just kind of seeks low energy states. But they utilized this reverse annealing protocol where you start in a given state and then you go back to the quantum critical point and then you wait and then you come back out again. And this allows you to very precisely control how much thermal and quantum fluctuation you have in your system. And they studied the model like in this reverse annealing regime and swept a lot of parameters to see what would happen. Now, I want to show you the synthesis of three different data sets, which piqued our interest and we found to be quite fascinating. So we have the three different data sets, the quantum Monte Carlo data set on the left, the quantum annealing-based data set in the middle, and then the real laboratory data on the right. Essentially, you have to pull out three specific curves in this data and then rescale them so they're on the same energy scale, and then we can compare them side by side. And that's what I'm going to show you on the next figure. So this is the key figure for the material. The black dots in the figure are the real experimental data. The green dots are the best fit that was produced by some quantum Monte Carlo simulation. And the pink dots were the best fit that was produced by the surrogate model in the quantum annealing platform. So first off, we can see that there's like a qualitatively better match for the quantum annealer, right? So the pink dots are like much more well aligned with the black dots. Additionally, running this experiment on the quantum annealer was faster than doing it in the laboratory or running the quantum Monte Carlo simulation. So it seems like there's a potential speed advantage there as well. But I think the thing that is most exciting about this potential match is that we can make observations with quantum annealing that are not possible to be made in the laboratory, especially with respect to these metastable states. So in that same paper, there are some beautiful visualizations of the configurations of the spins in these different states. And I'm focusing in on the middle metastable plateau. If you compute the ground state of the material at this particular energy level, it will have a long-range order. So if you look at the red plot, that's kind of showing you that the configurations of the spins have a similar pattern across the whole material surface. But what we see for the data from D-Wave that matches the experimental data is a very different picture, which is this one with like the blue and the green. Essentially, you have islands of structure that are large, but don't span the whole region of the material. And so this maybe gives you a hint of what's going on in these metastable regimes. There could be like islands that are kind of moving in around the material, but don't ever resolve to being like all the same way. And this is exactly the kind of insights that would dramatically speed up the rate at which we could do scientific discovery with a simulation capability. So we believe at Los Alamos that these results provide strong evidence that current quantum annealers are sufficient for supporting magnetic material discovery. And consequently, we have started a new project. It's a fairly big effort at LANL called Accelerating Scientific Discovery with Quantum Annealing, where we want to bring together quantum annealing computer scientists like myself with theorists like Cristiano and experimentalists like Ming Sung, and really try to do this whole material discovery workflow together as one integrated whole. All the results I showed you before were kind of picked from different papers and put together, and it was like, oh, that's really surprising that all worked out. But if we all do it together and we synchronize all the results, then we can make really deep insights into these materials. Our grand challenge in this problem is to identify new spin liquid candidates. Quantum spin liquids are, to this day, debated if they even exist in real life. So this is a grand challenge, I promise you. But we do think we have a good chance to do it with this technology. So I'll just give you a bit of kind of how it works. So how will scientific discovery actually happen? One of the first insights we've had is that we need to start with a material sample. So we're going to begin with Ising-like materials, which aren't well studied because they haven't had a good simulation capability to back them up. And these are produced by material growers, and they're kind of the experimentalists figure out which one of these are possible. That particular material sample has an implied Hamiltonian. That's a lattice structure with certain interaction strengths that are determined by the crystalline structure of that material. So we build the Hamiltonian. Then we try to understand the properties of that Hamiltonian using simulation capabilities. Now, typically, this step would be done just with classical computers, but now we have a new tool in our toolbox, the quantum annealer, and I showed you how it can produce really interesting insights in the condensed matter theory before. So we do that, and then that generates some hypothesis of what we should see the material do under a particular experimental protocol. So we generate a hypothesis of a weird behavior the material should have. We go back to the laboratory with our real sample, and we test it in the laboratory. Now, most likely, at this point, the laboratory experiment does not match our hypothesis. So then we revise our Hamiltonian or some assumptions we have about the material, and we iterate this loop over and over and over again. Eventually, if at some point the real experimental data matches the data that comes out of all the computer simulations, then we have really strong evidence. We have a deep understanding of what's going on in the material. That is really the exciting, super challenging thing we're trying to do right now. So just to wrap up, I gave you the pitch in the beginning, but I do believe that quantum annealing and analog quantum computing more broadly is not a transitional technology. I think it's really here to stay, and it'll be useful for the subset of applications it really fits well for a long time. My experience using D-Wave systems is that it's a really fast computer for quantum simulation. It's amazing how much data it can produce on the timescales you get it. The challenge we always face when we're doing physics simulation with these platforms is finding this beautiful match between application and what the computer can do. But we think we've identified at least one really nice class of applications at Los Alamos in this magnetic material discovery context. So with that, I'll thank you very much, and I'm happy to take questions during the breaks anytime.